Okay, so welcome to the third online class of probability. So we'll keep talking about in this class about random variables, and we'll specifically be talking about discrete random variables. Okay, so these are given our probability triple XFP. The discrete random variables are going to be, we're going to denote it by x. They're going to be functions that are going from omega to a set S, which is countable, and it's a subset of the real numbers. Okay, for discrete random variables, we had seen is that they take values. Okay, so we're going to say that S is equal to S1, S2, and so on, countable number. And so for each S1, S2, and S3, we have the probability function. So the probability function f that is going from S to 0, 1 associated to x is given by P, the probability of x is equal to Si, is f x of Si. Okay, so knowing the probability distribution f x of a given random variable completely characterizes how it behaves. Okay, so in general, just in notation, so what we need for these random variables, we can actually get the probability of x being equal to a specific value. So with respect to what we had said in the other class, so definition. Two discrete random variables x and y are independent if the probability that x is equal to a certain number and the intersection, the probability that y is equal to a certain number, has to be equal to the probability of x equals to x times the probability of y is equal to y. Okay, so this is the definition of independence. When you have discrete random variables, you can actually check that this is equivalent to what we did last class. Okay, so let's look at an example that at the beginning seems fairly intuitive, but then it'll become a little counterintuitive. Okay, so example. So let's say that we flip a coin n times. X is the number of heads and y is the number of tails. Okay, so these random variables should be distributed the same way, and it should be a binomial np. But so the question is, are x comma y independent? And the answer is no. Comma. Okay, so how can we check this? We can check this fairly easily by checking, okay, so what is the probability that x is equal to n and that y is equal to n? Okay, this is equal to 0. If you flip a coin n times, you cannot have n heads and n tails. Okay, so this is an impossible event. On the other hand, if we have the probability of x is equal to n, this is equal to 1/2 to the n, and the probability of y is equal to n is the same 1/2 to the n. So the probability of x equals to n times the probability of y is equal to n is equal to 1/2 to the 2n, which is different from 0. Okay? So these guys are not independent because once you have set the number of heads, the number of tails has to be completely determined because we are flipping a coin n times. And what we have is that x plus y is equal to n. So whenever you have a condition like this, you will never be able to have that x is independent from n. Okay, but let's look at something that is slightly more complicated. Let's assume we flip the coin a random number of times. Okay, so here we are flipping the coin not a fixed number of times. We are not flipping it n times. We are flipping it a random number of times with distribution given by Poisson lambda. Okay, so the Poisson lambda is the distribution we saw last class. So the distribution is given by the probability that n, this is the number of flips, is equal to k. This is distributed, so the probability that n is equal to k, this would be e to the minus lambda times lambda to the k over k factorial. Okay, so in this case, the number of heads is independent from the number of tails. Okay, so x and y are independent. So one of the things that we have is that x plus y is equal to n. So now we need to, let's say that we want to find the probability that x is equal to little x intersection, okay, so I'll write it like this, y is equal to little y. Okay, so in notation, just for you to get used to this, this would be x equals to x, comma, y equals to y. So the probability that we have little x heads and little y tails is the same as the probability that we have x heads and we flip x plus y times. Okay, this is because we are using this property here. Okay, but at the same time, this probability, so already here, the probability that x is equal to x, comma, n is equal to x plus y, here we can use conditional probability that say this is the probability that n is equal to x plus y times the probability of x is equal to x given that n is equal to x plus y. Okay, so this is the probability that you got x heads given that you flipped x plus y times. Okay, so the probability we got x heads given we flipped the coin x plus y times. Okay, so now these two probabilities we can compute explicitly, because the probability that n is equal to x plus y, this is going to be equal to replacing k by x plus y. So this is going to be e to the minus lambda, lambda to the x plus y over x plus y factorial. And now the probability that we got x heads given that we flip the coin x plus y times is going to be 1/2 to the x plus y times the combinatorial number x plus y x. Okay, so how many in a set of size x plus y, how many ways I can choose a subset of size x? Okay, and then this is divided by the quantity of possible combinations, that is 2 to the x plus y. Okay, so this guy here is distributed with binomial. This is distributed with the binomial of, here would be the binomial x plus y 1/2. Okay, compared to the last class. Okay, so this is the value at x. Okay, so now expanding this a bit, what are we going to get? This is e to the minus lambda, lambda to the x plus y, and then here we have x plus y factorial over x plus y factorial times x factorial times y factorial times 2 to the x plus y. Okay, and the factorials of x plus y disappear. Now, okay, so this is this probability. I'll write it just to have it in a clean form. X plus y is lambda over x factorial, y factorial, 2 to the x plus y. Okay, so now what we want to check is that we have flipped the coin random number of times. This is the same as the probability of x is equal to x times the probability of y capital Y is equal to Y. Okay, so is this actually equal? Okay, so what are we going to do? We are going to separate our space into infinite countable pieces. So the probability that we get x heads is going to be the sum over the number of flips. Okay, so we are decomposing on the number of flips. So this is the sum of, let's call n equals to 0 up to infinity of the probability that x is equal to little x, given that we have flipped little n times. Okay, so one thing that we should note is that if n is less than x, then the probability of x equals to x given n equals to n is equal to 0. Okay, if we have flipped the coin one time, we cannot get 3 heads. Okay, so only if we have flipped the coin at least 3 times, we'll be able to have a positive probability here. Okay, now using Bayes' rule, this is going to be equal, so now I can put the sum from n bigger or equal than x. The probability that n I flip little n times the probability that x is equal to x given we have flipped n times. Okay, but now these things we can compute. This is distributed Poisson lambda, and this is distributed binomial, and here it would be binomial n 1/2. Okay, so this is going to be the sum of n bigger or equal than x of lambda to the n e to the minus lambda over n factorial, and then this is going to be the combinatorial number n x times 1 over 2 to the n. Okay, so now the only thing that we need to check is like compute a bit more to actually get the expression that we had before. So we can actually have to sum these things up. So how do we sum these guys up? Here we have a bit of a cancellation. Here we have the sum n bigger or equal than x, lambda to the n, e to the minus lambda over n factorial times n factorial over n minus x factorial times x factorial multiply by 1 over 2 to the n. Okay, so here we just get, if we take the terms that don't depend on n outside, we're going to get e to the minus lambda over x factorial, and the sum n bigger or equal than x, lambda to the n, lambda over 2 to the n times 1 over n minus x factorial. So what you can do is change the variables in your summation by taking a new variable m, which is a n minus x. So, okay, so this is changing variables. There's a few ways of doing this. I guess this is the clearest one for me. So then this is going to be equal to e to the minus lambda over x factorial times the sum of m bigger or equal than 0 of lambda over 2 m plus x over times 1 over m factorial. So if we take the lambda over 2 to the x outside, we get e to the minus lambda x factorial times lambda over 2 to the x, sum of m bigger or equal than 0, lambda over 2 to the m times 1 over m factorial. This term here is exactly the exponential term, which is e to the lambda over 2. So simplifying everything, we get that this is e to the minus lambda over 2 times lambda to the x over x factorial times 2 to the x. Okay, so the probability that x is equal to x is given exactly by this, and so we can actually check that the probability that y is equal to y, this is completely analogous, and it would be e to the minus lambda over 2, lambda to the y factorial times 2 to the y. So if we check the expression that we had gotten before, we get that if we multiply p of x equal to x times p of y is equal to little y, this is going to be equal to e to the minus lambda, lambda to the x plus y over x factorial times y factorial times 2 to the x plus y, which is equal to the probability that x is equal to x, comma, y is equal to y. Okay, so the point of this being is that even in this simple example in which you would expect that a relationship of x plus y is equal to the number of flips is killing any sort of independence, once we choose to flip the coin a random number of times, something to be so correlated like the number of heads and the number of tails are actually independent from each other. Okay, so this was just an example of something that seemed fairly simple, but actually can be a little bit involved, okay? All right, so from random variables, a couple of things that are fairly important is some quantities we can compute from them. One of them is the esperanza, in Portuguese, the expectation. Okay, so of a random variable. So if we run an experiment, we can have an expectation of what is the value that is going to come up. Okay, so if we are measuring the height of people in a city, we would expect that the value is going to be around a meter and 70 centimeters and a meter or 60 centimeters, but we know that it's going to be above a meter. Okay, so a way of sort of quantifying this is starting to look at what would be the expected value of a certain random variable. Okay, so in general, of a given experiment, we could actually just take the average. Okay, so if we have data points, x1 through xn, we can consider consider the average. So the average, which in general we are going to denote by mu. Mu is going to be the sum of x1 plus x2 all the way to xn divided by n. So for random variables, we have an analogous definition, which is the expectation. Okay, so definition. The expectation of a random variable let's do it of a discrete random variable with, so let's say a discrete random variable x with a probability function f(x) is given by and this is usually denoted by this, the expectation of x is going to be the sum over all the x such that the probability function is positive of x times f(x) of x. Okay, so this is basically the sum of over all the values that your random variable can take, weighted by the probability. Okay, so if your random variable takes really large numbers and really small numbers, you have to weight by what is the probability that each one of these numbers appears. Okay, so this is a weighted average over the possible outcomes of x. Okay, and a remark, okay, so, and the point is, this is only valid when the sum is absolutely convergent. Okay, so we'll see an example later on, but the point is that this guy needs to be well defined. Okay, so let's check a lemma on this, and this is the usual thing that we are trying to do. So if we have a definition for a random variable, then we can do the same definition for a function of a random variable. So let's say let x be a random variable with a probability function f, and let's say f of x, and g from R to R is a function, is a given function. Then the expectation of g of x is equal to the sum over x such that fx of little x is positive of g of x times fx of x. Okay, so the remark is we can compute the expectation of functions of random variables. Okay, so one of the things I guess I didn't say at the beginning is that we are interested in the expectations of random variables because they are easy information to get, and sometimes they encode a lot of the things that we want to figure out from a specific situation. So knowing the expectation of a random variable, it will help you solve a lot of problems that we are going to be doing. Okay, so the point is sometimes you can rewrite the question in terms of an expectation of a random variable that you can actually calculate, and the properties that we're going to be looking about expectation will help you to calculate the expectation in particular cases. Okay, so let's go for the proof of this. Okay, so as we have said before, if we have a function of a discrete random variable, so g of x is also a discrete random variable. Okay, and so let's look at this a bit more. So what is the probability so given y in R, we can look at the probability of g of x is equal to y. Okay, but now the probability that g of x is equal to y is the same as the probability that x is in the inverse image of y. Okay, so this is the inverse image of y. So okay, so g minus 1 of y is a set is equal to all the x's in R such that g of x is equal to y. So then the probability that g of x is equal to y is going to be the probability of x is in g inverse of y which is going to be the sum of x in g inverse of y of the probability function f of x x. Okay, so this guy here is f of gx at y. So f of gx at y is the sum of all the preimages of y of f of x x. Okay, so yeah, this is the set set of pre-images. Okay, so now let's try to compute the expected value. So computing expected value, we have that the expectation of g of x is going to be the sum over y of y times the probability that g of x is equal to y, which is equal to the sum of y, the sum over y of the sum over x, the sum over x in g inverse of y of f of x. Okay, but this guy here, x is in the pre-image of y, is equivalent to saying that, okay, so x is in g inverse of y if and only if g of x is equal to y. Okay, so here we have y times the sum of x in the g inverse of y, f of x. This guy, by using this property here, is the same as the sum over x of g of x times f of x. Okay, so this would be like exchanging the order of summation. Okay, so if we sum first over x and then over y, we can actually decompose it into realizing that this is the sum over x of g of x times f of x. Okay, and the whole thing is to use this property here. Okay, so that's one of the first properties of the expectation. The other simple properties, and let's call it, let's keep this a proposition. So properties of the expectation. So one is, if x is positive, then the expectation of x is also going to be positive. The second one is, if x is equal to a constant almost surely. Okay, this guy stands for almost surely. Then e of x is equal to the constant. And the third property is that the expectation is linear. So if we take a, which is a real number, times x plus b, okay, so this is this is like the function we have done before. This is going to be a times e of x plus b. And let's do one more. So this is the simple version. The slightly harder version, which is what we're going to do, is going to be the expectation of ax plus b plus c times y is going to be a times the expectation of x plus b plus c times the expectation of y. Okay, so this last property says that expectation is a linear operator. Okay, so given sums, okay, so these guys x and y are random variables. So if we take sums of linear combinations of random variables, we still get we get that the expectation is linear on the sums. Okay, so we can pass the expectation inside the sum. Okay, so let's do the properties. So the first one is that if x is bigger than 0, then x is expectation is positive. So the expectation of x is equal to the sum of x such that fx of x is positive of x times fx of x. Okay, but this guy here, so if x is positive, then fx of x is positive. F of x being positive implies that x is bigger or equal than 0, which then this implies that this is equal to the sum of x positive f of x bigger or equal than 0 of x times fx of x. Okay, but now this guy is positive, this guy is positive, everything is positive. Now, for the second one, we are going to look at the case where the random variable is equal to a constant almost surely. And in this case, we want to say that the expectation is equal to a constant. So in this case, what is the expectation? The expectation, so what is the probability function of f? F of x. So fx is going to be equal, so let's call it fx of x is going to be 1 if x is equal to 0 to c, and it's going to be equal to 0 otherwise. Okay, so if we take the expectation of x, this is the sum over the x such that fx of x is positive of x times fx of x, and this is just going to be equal to c times 1, which is equal to 0. Okay, now let's just 3 follows from 4. 3 follows from 4. So let's just take a look at 4. Okay, so here we have x, comma y, discrete, random variables, and we consider z to be equal to ax plus b plus c times y. Okay, so this is a random variable. This is a new random variable, which is also discrete. And then we have that z is in the little c. Let's call it like this. Little c is in the image of capital C if and only if there exists little x in the image of capital X and little y in the image of capital Y, such that a times little x plus b times c times little y is equal to little c. Okay, so we can define this set S of little c, which is equal to all the x comma y such that ax plus b plus c times y is equal to little c. Okay, so now if we want to calculate the expectation of z, the expectation of capital C is going to be the sum of z, little z in the image of capital C of little z times the probability that capital Z is equal to little c. But the probability that z is equal to this little z is going to be the same as the sum of z in the image of capital C times of c times the probability of the pair x comma y is in the set S little z. Okay, but now because so using that x and y are discrete, we have that the probability that the pair x comma y is in S little c is going to be equal to the sum over the little x comma y in S little c times the of the sum of the probabilities that x is equal to little x and y is equal to little y. But again, this is the similar case as before. So here we would have the expectation of z is equal of capital C is going to be the sum of little c of z times the sum over x comma y in SC of the probability of x equals to x comma y is equal to little y. But now this can be written so this is similar to what I was doing for the function of a single random variable, but this is a function of two random variables. So this condition here can be put into the sum. Okay, so this is the sum over little z of z of the sum over x comma y of z times the probability of x equals to x, y equals to y, times the indicator that ax plus b plus cy is equal to little z. Okay, so this thing here has been transformed into this indicator. So once you're able to add the indicator, now you can start playing, because now you can switch the order of these things, and now we can take the sum over x comma y of the probability of x is equal to little x comma y is equal to little y of the sum over z of the indicator of ax plus b plus cy is equal to c. But this guy is 1 if and only if ax plus b so this would be the sum over c of z times the indicator of ax plus b plus c y is equal to little c, but this will only happen when c is equal to this number, and this is the only active term in this sum. So then you get the sum over x comma y of the probability of x equals to x times y is equal to y times ax plus b plus cy. And now what we have to do is split this sum into the sum over x and the sum over y, and then realize, I mean, here we can, all of these sums are assumed to be absolutely convergent, so we can do all of these manipulations. So what we can write is that this is equal to, and now we decompose into the different terms. This is going to be a times the sum over x of x times the sum over y of the probability of x, capital X is equal to little x times capital Y is equal to little y. Now plus b times the sum over x, the sum over y of the probability that x is equal to little x, the probability that y is equal to little y, plus c, and now I'm going to sum first over y, I'm saying on the outside over y times the sum over x of the probability that x is equal to little x, comma, y is equal to little y. Okay, so I have written the sums like this because this guy here, if you sum over all the possible values of y, the projection onto the first variable is going to be the probability that x is equal to little x. And similarly, if you sum over x first, this probability is going to be the probability that capital Y is equal to little y. And this guy here, the sum over x and y over all the possible values of x equals to x and y is equal to y, has to be equal to 1, okay, because that's the probability of the full set space, okay. This is equal to 1. So if you put everything together, this would be a times the sum over x of x, the probability that x is equal to little x, plus b plus c times the sum over y of the probability of capital Y is equal to little y. Okay? But this first term is equal to a times the expectation of x plus b plus c times the expectation of y. Okay, so what we have started with is the expectation of ax plus b plus cy, and we have gotten a times the expectation of x plus b plus c times the expectation of y, which is what we wanted to prove. Okay, so the idea is that this is giving you that the expectation is linear. Okay, so if we take the expectation of a sum of random variables, they will be the sum of the expectations. Okay, and you don't need any independence or anything for this. Okay, so this is one good thing to have when you're trying to compute expectations. Okay, so that's enough of expectation for now. The second thing that we need to talk about how a random variable behaves is the variance. Okay, so the second topic is variance of a random variable. So so the expectation gives you the likely value that you're going to get out of an experiment, but the variance gives you how far away are you going to be from that likely value. Okay, so how likely is it you're close to this likely value versus some value which is really far away. Okay, so let's say, let's define this. So definition, let x be a discrete random variable, then the variance, so it's usually called sigma, so sigma, this would be sigma squared, which is equal to the variance of x, is equal to the expectation of x minus the expectation of x squared. Okay, so this is another random variable. This is another discrete random variable. And we take the expectation of this thing. So, okay, so this is how much, this is the expectation of the square deviations from the expected value. Okay, so what are simple observations of this? So an observation is sigma squared is always positive. Okay, and this is because of the property we have just shown. This guy here is always positive. So whenever you take expectation of a discrete random variable which is positive, you're going to get positive. The other thing that you should notice is that sigma squared is equal to 0 if and only if x is equal to the expectation of x almost surely. Okay, so sigma squared is equal to 0 if and only if x is a constant random variable. Okay, so you have variance 0. I mean, this this already tells you how it's good. So the variance is measuring how far are you from a constant random variable. So the larger the variance, the farther you are from being a constant. Okay, so let's look at some properties. Okay, I actually forgot to tell you something, but let's do that in a second. So let's look at some properties. So theorem. So what is one property? The variance of ax is equal to a squared times the variance of x, and b is the variance of x plus y for two different random variables is equal to the variance of x plus the variance of y. Okay, and so this is when x comma y are independent. So actually we only need x comma y not to be correlated. Okay, so I'll go back to the proof of a theorem in a second. So, but the definition is the following definition: x comma y are set not to be correlated if the expectation of the product x dot y, x times y, is the expectation of x times the expectation of y. Okay, so there is no reason why the expectation of x times y has to be equal to the expectation of x times the expectation of y. For instance, in the example, let's say that we flip a coin one time. So let's put an example. So let's say we flip a coin one time, and x, as before, is the number of heads, and y is the number of tails. So x plus y is equal to 1, x is bigger or equal than 0, and y is bigger or equal than 0. Then x times y is going to be equal to 0 almost surely. Okay, so because if x is equal to 1, then y is equal to 0, and this product is equal to 0. And similarly, if y is equal to 1, then x equals to 0. But now, so then the expectation of x dot y is going to be equal to 0, which is different from the expectation of x times the expectation of y, which is equal to 1/2 squared. Okay, so what happens with these random variables? They are not, as we saw before, they are not independent. So what we are going to do, just to see that like this is valid when x and y are independent, so we're going to have the following lemma. If x comma y are independent, then they are not, then they are not correlated. Okay, so what is the proof of this? So if they're independent, what we get is that the probability of x equals to x, comma, y equals to y is equal to the probability of x equals to x times the probability of y is equal to little y. So then the expectation of xy is the sum over x comma y of x times y. So for this expression, so you should look back at the proof of linearity. So you have to look at the sum, so you should call this equal to z, and then you have to look at the set as z, which is equal to all the x comma y such that x times y is equal to z. But if you decompose all of this, you are going to end up that using the properties that we saw before, the expectation of x times y is going to be the sum of x comma y of x dot y times the probability of x is equal to little x and capital Y is equal to little y. Okay, so using this property here, we are going to get that this is going to be the sum over x of x times px equals to capital X times the sum over y of y times the probability of capital Y is equal to little y. But this guy is nothing like but the expectation of x times the expectation of y. Okay, and this finishes the lemma. Alright, so this lemma was just to show that whenever we have x and y that are independent, then they are not correlated. So the expectation of x times y is equal to the expectation of x times the expectation of y. So now let's prove the theorem. So we're going to prove the theorem. So we're going to prove that the variance of a times x is a squared times the variance of x, and the variance of x plus y is equal to the variance of x plus the variance of y whenever x comma y are independent. So let's go with proof of the theorem. So A, if we take the variance of a x, this is going to be by definition the expectation of a x minus the expectation of a x squared squared. But now, sorry, the square is here. So, but now the expectation of ax is a times the expectation of x by linearity. So then what you get is that this is equal to the expectation of a squared times x minus ex squared. But again, by linearity. Okay, so here is by linearity. And here again by linearity. This is equal to a squared times the expectation of x minus e of x squared. And this is equal to a squared times the variance of x. Okay, so that's for part A. Now for part B, we should take the variance of x plus y and now use the definition, and this is the expectation of x plus y minus the expectation of x plus y squared. Okay, so one of the things is that this guy here is the expectation of x plus the expectation of y. Okay, so we can rewrite this as the expectation of x minus e of x minus, or here would be plus, y times e of y, all of these squared. But now if we expand the squared and use linearity, this is equal to the expectation of x minus e x squared plus the expectation of y minus e of y squared, and then plus, and I'm missing a term here, which is the cross term. So let's put it here. So this is dot 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 plus the cross term 2 times the expectation of x minus ex times y minus ey. Okay, so this term here is the variance of x. This term here is the variance of y. And now I want to show that if x and y are uncorrelated, this thing is equal to 0. So now we need to expand this multiplication. This is going to be the expectation of x times y minus e of x. So minus the expectation of x times e of y minus the expectation of e of x times y plus the expectation of the number e of x times e of y. Okay, so the idea is again to use the linearity of all of this. So you expand all of these terms and now you take the expectation, and now what you're going to get is this is the expectation of x times y minus these two terms plus this term. All of these three terms are equal to the same thing. This guy is equal to the expectation of x times the expectation of y. This is equal to the expectation of x times the expectation of y, and this is also equal to the expectation of x times the expectation of y. So what we're going to get is that this term here is equal to all of this term here is going to be 2 times expectation of x times y minus expectation of x times expectation of y. Okay, so what we can write is a slightly more general theorem which says that the variance of x plus y is going to be equal to the variance of x plus the variance of y plus 2 times the expectation of x times y minus the expectation of x times the expectation of y. So this is equal to 0 whenever x is independent from y. Okay, so is equal to 0 if x comma y are independent. Okay, and just one thing that we should be careful is that, I guess I didn't mention it at the beginning, but I should have mentioned it a while ago, is that the expectation that of a random variable is not always well defined. So, for instance, I mean, let's say that we take x, which is a discrete random variable, such that the probability that x is equal to the number 2 to the I is equal to 1 over 2i for every I in n. Okay, so then if we take the expectation of x, this is going to be the sum over I of 2 to the I times 1 over 2 to the I, which is just equal to the sum of 1, which is equal to plus infinity. Okay, so in this case we could still make sense of the expected value as saying it's plus infinity. Okay, so you have that the expected value is going to be not finite, but there are some cases in which you cannot even make sense of what the expected value should be, because you could take the probability that x is equal to k to be equal to a over k squared for every k in the integers minus 0. So in this case, so the expectation of random variable is not always well defined. So in this case, we would take a to be equal to 1 over the sum over k in z minus 0 of k squared, which is like something like pi or pi over 2 or something like that. And so if we compute the expectation of x, the expectation of x is going to be equal to the sum over k in z of k times the probability that x is equal to k, which is equal to the sum of k in z minus 0 of a over k. Okay, but this sum is not convergent. So it's not absolutely convergent, and it doesn't have a natural extension to say that it's plus infinity. So this guy, the expected value of x, is not well defined. Okay, so this is what I wanted to say for today, and later I will upload another video of the next class. Thank you.